Okay, the book provides a brief introduction to climate change, evolution, and some modes of climate, as well as climate change. I'm going to run through it. There are lots of detailed podcasts on this in my other courses, so if you're a climate person doing this course as climate and health, then you may want to catch up. If you're a health person, then maybe you are okay with this brief introduction, or you can also add more details from the other podcasts. This is a nice figure made in this paper that appeared in the Proceedings of National Academies of Sciences, which is concatenated the temperature records going all the way back to about 62 million years ago, or 65 million years ago or so, just at the end of the dinosaur era. So here we have Paleocene, Eocene, Oligocene, Miocene, and so on, coming into the Holocene. Multiple sources and multiple resolutions, multiple reconstructions are put together, but we will use it just to say that climate changes all the time. So you know that we have been very warm in the past during the dinosaurs, and then we've been on a cooling trend for a while, and then global warming is taking us towards this direction. We've had very rapid warmings on a short time before the Paleocene, Eocene thermal maximum over here, but the warming rates we are having now are faster than this in terms of how short a period over which these are happening, which obviously is very important for species who cannot adapt to such fast warming rates. There is the early Eocene, mid-Pliocene, and you can see that temperatures have changed all the time at various time scales. Why does it matter? Now we are going into global warming, which is still less than the warmth here on a global average, because we have only evolved in this period here, so it's mostly about us. The planet is not going anywhere. Many species will go extinct, but some will survive as they have done in the past, and so on and so forth. So we talked about the Pliocene, Pleistocene changes where human evolution happened. So there is some relation between species evolution and climate change always. Climate change is a driver of evolutionary adaptation traits, which we looked at. And this is the relatively stable period over which we became modern agricultural human beings, and then coming into the Common Era, we started the Industrial Revolution, and we are increasing greenhouse gases. Here we are looking at 2005, and then depending on what paths we choose for the future in terms of energy, population, technologies, consumption, methods of doing agriculture, production, traveling, etc., we will go into various regimes of warming here relative to the modern period. Typically these are anomalies with respect to the 1961 to 1990 period, but sometimes they are not the same baseline. Nonetheless, the main point is that climate is restless, and it is always associated with new niches opening up, new species adapting to temperature and precipitation and light niches and oxygen levels and so on and so forth. From Britannica, Encyclopedia Britannica, I took these about biodiversity of marine animal families over geologic period. So this is going to Precambrian. If you remember your geologic times quickly, we had the Hadean, which is where it was hell, meteors bombarding primordial soup, no life, and then came Archean, which is the beginning, Arches, at 3.85 billion years ago or so. We have the first evidences of life, and then we had the Proterozoic, early life, and then we had Phanerozoic, which is the visible life, and the Precambrian is all the period before 540 million years ago, where various forms of life existed. So examples of marine life were severely affected by mass extinction events along the way. And we have all these periods, Cambrian, Ordovician, Tellurian, Devonian, and so on, coming up to the Neogene here. We are in the Quaternary here in the last bit. And various species have evolved along the way. Bryozoans, trilobites, jawless fishes, trilobites, brachiopods, You can see all these marine reptiles, and photosynthesis evolved around here, oxygen increased way before, around 2.4 billion years ago, but it wasn't at 100% of the current level. Over time it became the current level, and oxygen levels in the atmosphere had a huge impact on life forms, of course. So there is always an interaction between life and oxygen. Rise of oxygen is related to photosynthesis and life, and rise of oxygen affected other forms of life as well. Looking at the 650 million years ago to the present, this way, so we had first skeletal elements, first soft bodies, metazoans, first animal traces. There is details about radial symmetry versus bilateral symmetry, genes, and so on. First chordate fishes, metazoan families, vascular land plants, which drove down carbon dioxide, led to global glaciations like snowball Earth episodes. Then we had first amphibians, jawed fishes becoming diversified, reptiles, scaled trees, ferns, reptile diversity, major mass extinction, one of them at the PT boundary, another one happened at the KT boundary, meteorite crash, and so on. Flowering plants, birds, primate, extinction of dinosaurs, mammal diversity after the extinction of dinosaurs, and evolution of humans, which has happened at the last fraction of a second on this kind of a geologic time scale, right? So we arrived very late on the scene, but now we have evolved to be the most dominant force, like a geologic force. The climate change in the past have always been related typically to plate tectonics, mountain building, oceans reorganizing because of the plates moving, and so on. But there has always been also the orbital changes associated with Earth's orbit around the Sun. The shape changes on 100,000 year time scale called eccentricity. The obliquity changes at 41,000 year time scales, and the precession changes at 23,000 year time scale. So all those radiation changes, either distribution on the seasonal cycle or the amount received, together can create climate changes, building of glaciers, retreat of glaciers, which also affects vegetation, life, and hence pathogens, diseases, and so on. These kinds of details are probably not completely dealt with here because it's a very quick introduction, but essentially because Earth is a sphere, more radiation from the Sun per unit area is received in the low latitudes than at high latitudes because of the Earth's curvature. And then the outgoing long wave radiation, all the short wave radiation heats everything, evaporates, creates a greenhouse effect, and then energy is lost back to space. For equilibrium, incoming shortwave radiation has to equal the outgoing long wave radiation. It so happens that because of the shape, again, in the low latitudes we have more shortwave energy being received than long wave energy being lost, whereas at high latitudes there is an energy deficit because more energy as long wave is being lost to space. So unless you move energy from low latitudes to high latitudes, you will keep warming the tropics and cooling the poles, which doesn't happen, which means energy is being moved. So atmospheric circulation cells get set up like this. Warming leads to rising air, so-called intertropical convergence zone. Rising air takes moisture with it, expands, drops a lot of rain, and energy is being moved northward through these complicated circulations in the atmosphere. Clouds, rain, winds, cyclones, etc. And those winds generate ocean currents, and ocean also moves heat through the Gulf Stream, Kuroshio, and so on. So those are the kind of circulations that get set up, and we have with that dynamical reasons why we end up with things like the jet streams, the subtropical jet streams, polar jet streams, and so on and so forth. Map of the climate oscillation. So as we saw, climate changes at all time scales, but within that, because ocean can store heat and release heat as sun moves north-south with the seasons and rises and sets during a day, energy is being moved around and there are feedbacks in the system. So we end up with so-called oscillations. So we have things like El Nino, La Nina, North Atlantic Oscillation, Pacific Interdecadal Oscillation, Indian monsoon, and so on and so forth, which are essentially ways in which the heat in the ocean and by the atmosphere are being moved around at different time scales, which reorganize rain distribution, wind distribution, vegetation impacts, droughts, floods, heat, etc. So that also affects human beings and all species. So global temperature and carbon dioxide since the Industrial Revolution have increased. Carbon dioxide is easily measured, precisely measured, and it has increased monotonically, whereas temperature changes non-monotonically because some can go into the ocean, some goes into evaporating the ocean, some goes into melting glaciers, and so on. Okay, but what is obvious is that the temperature is increasing more monotonically now than before. You can see that it was cooler than the base period before about 1940. It was flat, that's the base period. Then we have been increasing, and now we are having warmer and warmer temperatures. And one of the ways to look at it as decades of warming. So you can see that even though the temperatures go up and down year to year, decade to decade they keep going up. Okay, so this is what human beings are doing. This affects life, pathogens, human ecology, human health. That's what we are after in this course in terms of how climate variability and climate change are part of the human ecology and human health. Okay, so that's a very quick run-through introduction to the climate that is very variable, and there are lots of details about ice ages and so on that we will talk about as we go along. Okay, so El Nino, La Nina, NAO, PDO, they all affect the human ecology, which is what is important to remember. Okay.